Hello and welcome to your favorite Sridevi Classes YouTube channel, where we inculcate interest and confidence in science and engineering education. Today in our playlist Class 12th Physics, in our subject Electrostatics, we'll discuss the imaginary concept used by Michael Faraday to depict electric field phenomena, and we will understand characteristic property and application of force lines for different charged configuration. Let's start. The concept of electric force lines. Electric force lines, topic of our study, have no real physical existence. That means surrounding these charges, the lines which we have drawn here or will explain further have no real physical existence. They won't exist. It's an imaginary concept given by great scientist Michael Faraday, and it is used for pictorial representation or visual illustration of electric field phenomena which exist surrounding charge, and they can explain so many electric field experience very well and even help us in mathematical manipulation. So we also count these imaginary force lines as electric flux and use flux density to correlate electric field intensity. So this concept of electric force lines is very useful. Electric force lines can be straight lines or curved paths. If we place a stationary charge in electric field, these lines represent direction of force on that charge. So force lines is a straight or curved path along which a stationary charge experience force if placed in electric field. Tangent drawn on straight line is that straight line only, and on curved line it will deviate its directions, and such tangential direction on force lines represent direction of electric field at the point where tangent is drawn on force lines. And one important thing is that if force line is a straight line, then stationary charge have initial acceleration and velocity along force lines, and further acceleration in the same line will make path along straight force lines. So as stationary charge follow straight force lines, but in case of curved force lines, initial acceleration will produce velocity in one direction, and curved path of force lines will change direction of electric field and direction of force on positive charge. So the particle will deviate its path from curved force lines. It will take some midway parabolic path. The density or number of force lines per unit crossing normal area, that we call flux density, represent the strength or intensity of electric field. For this positive charge at closer vicinity, in this green ellipse, the density of force lines is higher, so we can say electric field in this green ellipse is stronger, whereas electric field in cyan ellipse area, where density of force lines has decreased, the strength of electric field is lesser here. So tangent on force lines represent direction of electric field, and density of force lines represent magnitude of electric field. Some important properties of force lines are as follows. The force lines start from a positive charge. As for a solo isolated positive charge, they are radially outward, and they ends at negative charge. That means for a isolated negative charge, these are radial inward force lines as shown in this yellow highlight. For positive and negative isolated charge, force lines configuration is just identical, only arrow direction is different. For positive charge it is outward, and for negative charge it is inward. If a positive charge and electric charge of opposite polarity and similar magnitude are placed very close to each other, this configuration is known as electric dipole. And for electric dipole, force line starts from positive charge and ends on negative charge and form such typical configuration as shown again in yellow highlight. We can very well see that for this dipole electric field on line joining dipole charges called XII, electric field is directed from negative charge to positive charge direction to both sides, whereas this perpendicular bisector line known as quadrature axis, the tangent drawn indicate just reverse direction of electric field. In case of isolated positive charge, if I make two circle of different radius, this magenta got certain radius and cyan circle got double radius, both will have same number of force lines crossing their surface area, but the surface area of cyan circle having double radius is 1/4 of magenta circle. So we found that density become 1/4. So as we move away from isolated positive or negative charge, the strength of electric field or density of force lines decreases as inverse of square distance, whereas in dipole case, this force lines of positive charge divert toward negative charge, and we will find that that variation of density is inverse of cube of the distance from center point, and it is become 1/8 for double distance. For uniform line charge, again electric force lines are radial outward, just like that of isolated positive charge. But to have a difference, it is three-dimensional diversion, whereas for line charge, it is planar diversion. That means as we move away from line charge, electric field intensity will decrease, but it is just inverse function of distance. That means at double distance it become half. Whereas for isolated positive charge at double distance, electric field intensity become 1/4. This is again a great example where a positive charged body is enclosed in a metallic shell, and this positive charge have outward radial electric field lines, and there will be induced charges on this metallic shell, and inner periphery negative charge will become end of force lines, and outer periphery induced positive charge become source of again force lines. So we have a picture of force lines without any force line in metallic body. If two like polarity charges are placed to each other, then we'll find that force lines distribution is as shown in this yellow highlight, and it is quite clear that like polarity force lines will try to repel each other. So it make a sense that like polarity charge will repel each other. As you see here in dipole case, it looks that force lines try to make two charges closer to each other or form a attractive force in opposite charge, and there is a repulsive force in like polarity charge. One more interesting fact is, in this blue ellipse area, the density of force lines becomes 0. So it become a electric neutrality position, and we'll find that on two like polarity charge on joining line at one position, resultant electric field becomes 0. Electric force lines never form closed loop as shown here. If they form a closed loop, it means it is starting from positive charge and ending on a negative charge. At same identical position, opposite polarity positive and negative charge are in coexistence, and that coexistence of opposite polarity charge is not possible, as negative charge is excess of electrons and positive charge is deficiency of electrons, and such conditions will neutralize each other and only a surplus effect will act. So a point could have only a positive charge or a negative charge. Two charges can't reside together. So such force lines formation of closed loop is not possible. Whereas in case of magnetic force lines come out from north pole of magnet and enters on south pole, and within magnet they form closed loop from south to north. So they are always in closed loop because this north and south always exist in a pair. If we break this magnet to any smaller size, we found that a pair of north and south polarity will coexist in every tiny magnet. So as they two can't separate, north and south pole can't separate each other, so magnetic force lines are always in closed loop formation, and two opposite polarity charge can't coexist, so electric force lines are never in closed loop. Tangent drawn on force lines represent direction of electric field, and for a curved force lines, direction of electric field variation would be indicated by curvature of force lines, whereas for straight force lines the tangential direction and straight line would be the same, so electric field will be along that straight line. In case of straight force lines, that of isolated positive charge or a uniform charge density line charge shown here, whereas this field got variation of directions as per curvature. Between positive charge and negative charge parallel plates, electric field is uniform and it is indicated by parallel equidistance lines as shown here. But if electric field is not uniform and force lines are not parallel, even in that two force lines never cut each other, because as they cut at a point, the two tangent drawn at that cutting point indicate two different direction of electric field. As per uniqueness theorem, one point can't have two direction of electric field at one time instant. So if this two electric field direction of a point is not possible, then two curved force lines never intersect each other. Density of force lines passing per unit cross section area represent strength of electric field. Here at position A, force lines are closer to each other, they are dense. So electric field is stronger at position A as compared to position B in this non-uniform electric field. Whereas parallel equidistance lines as shown here in this yellow highlight represent an uniform electric field. That means at every position in this yellow highlight, magnitude and direction of electric field is the same. Behavior of conductor is very significant in electric field, and electric force lines are always normal to any conductor surface, whether it is flat or spherical or any irregular shape. And it is so as we can't have any component of electric field along surface. If there exists any component along surface, it will start drifting source charges, and in electrostatic, source charge movement is not allowed. Electrostatic is study of static condition, charge field effects. So electric field is always normal to spherical or flat surfaces, as here these radial lines by position of nearby conductor section get deviated, and again on the surface they are normal at entry and exit level, and they are also normal to spherical surface, and the same situation exists in this spherical shape at both positions. Electric field is normal to the surface because there should not be any component of electric field along surface. Another interesting phenomena about conductor bodies is that there will be no force lines inside a conductor body. Here I got a positive charge on rectangle conductor, and it will produce normal outward force lines, and there exists a semicircle conductor body in this electric field, and this conductor have induced negative charge on one side surface and positive induced charge on other side of the surface, and force lines end on negative charge, and there won't be any force lines inside the conductor, and they again start from positive induced charge to the other side of conductor. So we found that there won't be any electric force lines or electric field inside the conductor, because in electrostatic, if there exists any electric field in conductor, the free electrons of conductor will start drift motion, and movement of charge is not allowed in electrostatics. So in electrostatic studies, there should not be any electric field inside a conductor, so there won't be any force lines inside any conductor body. And in the absence of electric field, conductor body of any shape, size will behave like equipotential surface, and on every equipotential surface electric field can exist only on surface, that too normal. This powerful and informative learning video on force lines has explained the imaginary concept of Michael Faraday to depict electric field phenomena for different charged configuration, and you have also learned the behavior of conductor bodies in electric field. With this understanding of electric force lines, your understanding of electric field calculation will become better, and you can produce better and simpler description for electric field calculations. If you feel this study material useful, do share it with your friends, and for additional study material and online classes support, do join membership of Shridevi Classes YouTube channel. Thank you very much.